Download this code from codegive.com, link in the description below. OK, let's dive into Eric Weinstein's What If Ruby 3 talk from Rubyconf 2017. This talk is a fascinating exploration of potential directions Ruby 3 could take, focusing on type checking and static analysis to improve performance and developer experience. It's important to note that the talk represents a thought experiment more than a concrete roadmap for Ruby 3. The ideas presented are not necessarily implemented verbatim in Ruby 3 or later versions, but the concepts and motivations remain relevant. Context: the state of Ruby before Ruby 3. Before Ruby 3, which was released in December 2020, Ruby was primarily known as a dynamically typed language. This means that the type of a variable isn't explicitly declared, and the Ruby interpreter only checks types at runtime. This gives Ruby great flexibility and makes it easy to prototype and write code quickly. However, it also has potential downsides. Runtime errors. Type-related errors often aren't caught until the code is running, leading to unexpected crashes in production. Performance. Because the interpreter doesn't know the types of objects in advance, it has to make assumptions and perform checks at runtime, which can impact performance. Limited tooling. Dynamic typing can make it harder to build robust static analysis tools, like code completion, refactoring, and static error detection, that are common in statically typed languages. Eric Weinstein's core argument: a gradual type system. Weinstein's central idea is to introduce a gradual type system into Ruby. This means that developers would have the option to add type annotations to their code, rather than being forced to do so. This offers several advantages. Incremental adoption. Developers can start adding type annotations to critical parts of their code bases, gradually increasing the type coverage over time. They don't have to rewrite entire applications at once. Flexibility. Ruby's dynamic nature is preserved. Code without type annotations still works as before. Improved safety. Adding types to functions, classes, and variables can prevent many common runtime errors. Performance potential. Type information can be used by the Ruby interpreter, or a compiler, to optimize the code. Enhanced tooling. Type annotations enable more powerful static analysis tools, leading to a better development experience. Key concepts and examples from the talk. Weinstein covers a variety of ideas during his talk. Let's explore some of the most important ones. 1. Type annotations. Basic syntax. Weinstein proposed a syntax for declaring types using a leading colon. For example, what it means in this hypothetical system. Def add x, integer, y, integer declares that the add method expects two arguments of type integer and returns a value of type integer. Name, string equals Alice declares that the variable name should hold a string value. If you try to assign something that's not a string to name, a type error could be raised, either at compile time or runtime, depending on the specific implementation. Age, integer equals 30 similarly declares that age should be an integer. 2. Type inference. The goal. The type system should be smart enough to infer the types of variables and method return values in many cases, even without explicit annotations. This reduces the amount of typing the developer has to do. Example. If the type system can determine from the context that x is likely a number, it can infer a type for x and the return value of square without requiring explicit type annotations. 3. Duck typing and interfaces, structural typing. Asterisk respecting Ruby's nature. Asterisk Weinstein emphasized that any type system should respect Ruby's duck typing philosophy. Duck typing means if it walks like a duck and quacks like a duck, then it's a duck, meaning an object's type is less important than whether it responds to certain methods. Asterisk interfaces / structural typing. Asterisk the type system could support the concept of interfaces or structural types. This would allow you to define what methods an object must have to be considered a certain type, without requiring the object to inherit from a specific class. Asterisk example, hypothetical. In this example, quackable is an interface that specifies that any object passed to make _quack_ sound must have a quack method that returns a string. Both Mallard and Toy Duck implement this interface, even though they are different classes. For union types. Asterisk the problem. Sometimes a variable or method can have one of several possible types. Union types to the rescue. Union types allow you to specify that a variable can hold a value of one of several types. Example. In this case, string integer nil indicates that get_value can return a string, an integer, or nil. 5 generics, parameterized types. Code reusability. Generics allow you to write code that works with different types without having to write separate versions for each type. Example. Here, box T is a generic class. T is a type parameter that can be replaced with any type. When you create a box string, T is effectively replaced with string, and the get method is guaranteed to return a string. 6 compiler integration and tooling. Static analysis. A type system enables static analysis tools that can find type errors before the code is even run. Code completion and refactoring. Type information can improve code completion and refactoring features in IDEs. Performance optimization. A compiler can use type information to optimize the generated code. For example, it might be able to replace dynamic method calls with direct function calls in some cases. Illustrative code example, putting it together. Here's a more complete example that demonstrates how these features might be used together. Remember, this is hypothetical Ruby 3 code based on Weinstein's ideas. Important considerations and trade-offs. Complexity. Adding a type system increases the complexity of the language. Developers have to learn new syntax and concepts. Runtime versus compile time. The talk explored options for both runtime and compile time type checking. Runtime type checking is more flexible, but compile time type checking can catch errors earlier and enable more aggressive optimizations. Adoption. The gradual nature of the proposed type system is crucial for adoption. Developers can start small and gradually add types to their code bases. Performance implications. While type annotations can enable performance optimizations, there is also a potential for overhead if the type system is not implemented carefully. How this relates to current Ruby, Ruby 3.x and beyond. While Weinstein's exact syntax and proposals weren't adopted verbatim, many of the ideas have influenced the evolution of Ruby. RBS, Ruby Signature Definition Language. Ruby 3 introduced RBS, which is a separate language for describing the types of Ruby code. RBS files are typically stored alongside Ruby code and can be used by static analysis tools like typeprof. Typeprof. Typeprof is a static analyzer that comes with Ruby. It can infer types from Ruby code and find potential type errors. Sorbit. Sorbit is a static type checker for Ruby developed by Stripe. It's more strict than RBS and typeprof, but it can provide stronger guarantees about code correctness. It requires developers to add type annotations to their code. Gradual typing philosophy. The Ruby community has generally embraced the idea of gradual typing. The goal is to provide tools and mechanisms for adding types to Ruby code without sacrificing its dynamic nature. Conclusion. Eric Weinstein's What If Ruby 3 talk was a thought-provoking exploration of the potential benefits of adding a gradual type system to Ruby. While the specific proposals in the talk weren't implemented directly, the ideas about gradual typing, type inference, interfaces, and union types have had a significant impact on the direction of Ruby development. The current state of Ruby with RBS, TypeProf, and Sorbit reflects a commitment to improving code safety and performance while preserving the flexibility and expressiveness that make Ruby so popular. By exploring these concepts, the Ruby community has been able to create a more robust and versatile language.